Welcome to the video podcast series here at Ontario High School. We're going to look at balancing oxidation reduction reactions in acidic and basic solutions. In this first video podcast, we'll deal specifically with balancing in acidic solutions. This is generally an advanced placement chemistry topic, but is also taught in Chemistry 2 when we run a Chemistry 2 course here. And for some lucky students throughout the nation or world, you may well visit this in your introductory chemistry if your instructors move at a good pace. So stay tuned. The next two slides that you see will have the rules for balancing equations for reactions in acidic solutions. I recommend that you pause and write these down. So just pause the podcast, write these down, and then resume it. The first 5 rules are simply this. You divide the reaction into the appropriate half reactions. We'll talk about how to do that. Balance all elements other than hydrogen and oxygen. Balance the oxygen by adding water as necessary. And balance hydrogen by adding H plus as necessary. Balance the charge by adding electrons to the more positive side. And then multiply the half reactions. Well, that's on the next slide. We'll get to that one. Rules 6 and 7, which are the final 2 rules, will multiply the half reactions by the appropriate small whole number coefficient to ensure that the electrons lost in the oxidation half reaction equal the electrons gained in the reduction half reaction. And then we'll add the half reactions together, canceling species that are the same on both sides of the equation. Those are the rules. So we're now ready to go after this. Writing the correct half reactions is a key to solving this. The rationale we use is that it is useful when balancing to consider the oxidation and reduction reactions, referred to as half reactions, separately. So consider the following reaction in acidic solution, and once you go ahead and pause the podcast and write what you think the half reactions are, and when you resume, we'll take a look at the correct half reaction protocol here. Well, the reaction we're looking at is the dichromate ion, Cr2O7 2 negative, plus the chloride ion, and we're going to the chromium 3 plus ion and Cl2. So dichromate ion, you'll want to remember, is one of the strongest of the oxidizing agents we deal with, and halide ions such as chloride, bromide, iodide, these are often reducing agents. So the dichromate ion is the oxidizing agent, and the chloride ion is the reducing agent. Well, when we write these half reactions, the Cr2O7 2 negative will go with the Cr3 plus, the Cl minus will go with the Cl2. So here's our skeletal half reactions. Well, our first step is to balance the atoms. So in the Cr2O7 2 negative, the dichromate ion, we have 2 chromiums. So on the right side of the equation, we want to put 2 in front of the Cr3 plus. For the Cl minus going to Cl2, we have 2 chlorines on the right, and so we want to put a coefficient 2 in front of the chloride ion on the left. So we have 2 Cl minus will yield Cl2. We have oxygens present in the dichromate ion. So in this half reaction, we want to balance the 7 oxygens on the left side of the arrow on the reactant side with 7 waters on the product side. There is no oxygen present in the 2 Cl minus to Cl2 half reaction, so we're still in a holding pattern there. When we added the waters to the right side of the dichromate ion going to the chromium 3 ion on the right hand side, we also added hydrogen when we added those 7 waters. So we need to balance those 14 hydrogens that are involved in the water molecules on the right side of the equation. We'll balance those by adding 14H plus to the opposite or to the reactant side of the half reaction of the dichromate ion. Well, we have balanced for atoms. Now we want to balance for charge, and we're going to use electrons to do that. The first thing we need to do is find the charge on each side of these half reactions. For the dichromate ion, when we add 14H pluses to the side with the dichromate ion, we would take the 14 plus plus the 2 negative charge, and that would give us a total of 12 plus charges on that left-hand side. For the right-hand side, we take our coefficient of 2, multiply it times the 3 plus charge on each chromium, and that gives us a total of 6 plus. So for the dichromate ion half reaction, we have 12 plus on the reactant side and 6 plus on the product side. For the 2Cl minus going to Cl2, we take the coefficient 2 times the 1 negative charge, which gives us a total of 2 negative charges on the reactant side. And then our Cl2, any uncombined element, always has an oxidation state of 0. So we have 0 or neutral charge on the right-hand side. Now that we've looked at some of the charges on each side of these two half reactions, we can go ahead and add electrons to the side of the reaction that will bring balance to the charge. So since we have 12 positive charges on the left-hand side of the dichromate half reaction and 6 positive charges on the right-hand side, by adding 6 electrons to the left-hand side of that reaction, we can bring that charge to 6 plus, equaling the charge on the right-hand side. So we'll do that, and now our 6 negative charges from the electrons added plus 14H plus the 2 negative would give us a 6 plus overall charge. So we're balanced in the dichromate ion. On the chloride ion to chlorine half reaction, by adding 2 electrons to the right-hand side, we would bring a 2 negative charge to each side of that half reaction, and now not only are the atoms balanced, but so is the charge. The remaining issue that we have here, now that we've balanced for atoms and charge, is that our oxidation half reaction, the 2Cl minus going to Cl2 plus 2 electrons, has 2 electrons, whereas our reduction half reaction, 6 electrons are involved there. You can't have an oxidation-reduction reaction without the number of electrons in the oxidation half reaction equaling the number of electrons in the reduction half reaction. And you can recognize which is the oxidation half reaction because the electrons to balance the charge will be on the product side. For the reduction half reaction, the electrons to balance the charge will be on the reactant side. So what we need to do is multiply by a coefficient to achieve an equal number of electrons in both the oxidation and reduction half reactions. We can do that by taking a coefficient of 3 times the coefficients already present in the 2Cl minus yields Cl2 plus 2 electrons. So when this is balanced, we get 6Cl minus yields 3Cl2 plus 6 electrons. If you'll notice, the charges are still balanced, and now our oxidation and reduction half reactions have the same number of electrons present. Now that we've multiplied by coefficients to achieve the equal number of electrons, we can just look at the two half reactions, and we can see that we have the same number of electrons being lost as being gained. Everything is balanced for the number of atoms and the amount of charge. We're going to add the half reactions, and when we do this, we're going to cancel the species that are the same on both sides. When we look at this, we have 6 electrons on the reactant side of the dichromate half reaction, and we have 6 electrons on the product side of the chloride going to chlorine half reaction. So we can cancel those 6 electrons. Now, there are no other species in common on the left-hand side or right-hand side of these reactions, so that's all we can cancel. Since we've canceled the 6 electrons that were common to the opposite sides, we're going to go ahead and add these reactions together. And so you can see we have 14H plus the dichromate ion Cr2O7 2 negative plus 6Cl minus will yield 2Cr3 plus 3Cl2 plus 7H2O. After adding the two half reactions together, you want to recheck to ensure that the atoms and charge are balanced on both sides. So we can do a quick check of the hydrogen first. We have 14 hydrogens on the left. We have 7 times 2 is 14 hydrogens on the right. We have 2 chromiums on the left, 2 chromiums on the right. 7 oxygens on the left, 7 oxygens on the right, and then 6 chloride ions is balanced by the 3 Cl2 molecules. So we're balanced for atoms. We then add the charges up to make sure that they also remain balanced. So our 14 plus 2 negative plus 6 times 1 negative adds up to 6 plus. On the right hand side, 2 times 3 plus from the chromium ion equals 6 plus. So the equation is balanced for both the number of atoms and charge. Success. So here's our final balanced equation of the dichromate ion plus chloride ion in acidic solution. 14H plus Cr2O7 2 negative plus 6 Cl minus yields 2 Cr3 plus 3 Cl2 plus 7 H2O. Well, this is the end. I'd like to leave you with a quote from the great British statesman Benjamin Disraeli. Be amusing, never tell unkind stories. Above all, never tell long ones. I wish you well. Stay tuned for part 2 of this series. We're going to look at balancing oxidation reduction reactions that occur in basic solution.